Okay, so let us take an example. Evaluate the line integral x squared y dx plus y cubed the y along the closed path given by the space between the two curves. One curve is x is equal to y, the second curve is x squared is equal to y cubed. I have plotted the curve using mathematical. I'm surprised. I thought I showed the formula that I used to do the plotting. Okay, I made a mistake. I forgot to put that here, but in the next curve, I have that there. So you check, because I want you to be able to plot the curve yourself. The x is equal to y is the one in blue, and the x squared is equal to y cubed is the one in yellowish orange that you have there. So we are looking at an integral that goes along this path. When it gets to the joining there, it comes back. It goes through this, it binds this narrow strip of area. And that is the path. Now, so the given path is given, the path is given in the picture shown. Then the given integral is in the format of the Green's theorem. So we can write m of xy as x squared y and n of xy as y cubed. Consequently, doing the partial derivative of m with respect to y and the partial derivative of n with respect to x gives you x squared. That is idiot proof. That's very easy to do. So because if you differentiate this one with respect to y, you get x squared. If you differentiate this one with respect to x, you get 0. So the total thing is x squared. So that when you now do this integral, by the time you bring the line integral here, you have that this is integral from 0 to 1 dy, integral from y to power 3 over 2 y of x squared dx. And then, so there are two integrals here, and this is the key. On one, you integrate along x first, and then you come and integrate along y. The second one, you integrate along y first, then you come and integrate along x. And so the kind of questions I ask you in the exam, even though I will not ask you this full question, I can write this and write several things. I say, which one is it equivalent to? Just know that in the one case you're integrating with respect to the x direction, then later in y direction, and vice versa. That's how you get it. I will give 4 wrong answers and 1 correct answer, and it is for you to choose. It is only people who know how to perform this integral that will get the answers correct. So this is the answer now of this integral. There are 2 ways of performing this line integral here. So one way is to do it like this, and the other way is to do it like that. Now, so this is the second part, the right-hand side or the left-hand side, depending on how you do it, of the Green's theorem. Remember that Green's theorem has a double integral on one side and a line integral on the other side. What we have here is the double integral side. So we can get the answer by doing the double integral. And how do we do that? We now, I want to take the first integral. If I take the first integral, the way we get it is that we have this integral here, and then we can have integral of x squared. If you integrate x squared with respect to, if you integrate x squared with respect to what now? With respect to x here, I think I'm wrong here. It's s cubed over 3. Okay, there's an error here. Let me just correct that error. Luckily, the error only is in that point. So it is 1 over, there's 1 over 3 here, 1 over 3 s cubed. Okay, so this integral here, the integral of s squared is 1 over 3 s cubed, but this is being evaluated from y to power 3 over 2 to y. So you are going to substitute y to power 3 over 2, or when you substitute y, you get this. When you substitute y to power 3 over 2 negative, you get this. So, and then you are now going to integrate this complicated quantity now with respect to y. When you do that, the first expression gives you, minus 1 over 3 is out here. The first expression gives you y to the 4th over 4. That should be easy for you to do. And then the next expression, you know, you have to add 1 to 9 over 2. If you add 1 to 9 over 2, you get 11 over 2. and then you divide by 11/2. That's what gives you this expression. And when you work them, when you now substitute 0 and 1, which is the boundary of the integration here, you get 1/3, 11 minus 8/44, which gives you minus 1/44 by using the first integral there. When you take the second integral, again, you start by saying that this is x. We are integrating x squared with respect to y. If you integrate x squared with respect to y, as far as y is concerned, that x squared might as well be a constant. So it is simply x squared y. That because you are integrating in this first integral, you are integrating with respect to y. So that's why it is x squared y. And but the boundaries of the integral is variable x. So you're starting from x to power 2/3. So when you do that, you can now integrate. When you substitute, you have this one, x squared plus x squared times x to power 2/3 is what gives you x to power 8/3. The second one is x squared times x. That is why you get x cubed there. If you substitute again from 0 to 1, you get this expression, which is 1/4/311, which is again minus 1/44, showing that this integral here and this integral are exactly the same integrals. So you have done that now by taking a look at what is happening on the right-hand side of this expression. So on the right-hand side of this expression, you can integrate it on the plane. And when you integrate it on the plane, you can go x first and then y, or you can go y first and then x. That is why you have two expressions for this. So what we are going to do next is that we're going to take the path integral directly, the line integral directly, and see whether we can still get the same answer. You can see y minus 1/44 is the correct answer. So again, I also used the mathematical. I just coded that integral in the previous page using mathematical, the two of them, and again, mathematical spits out to me 1 minus 1/44. It is instructive and not rigorous to manually integrate. The two integrals are performed in the above code using mathematical. The right-hand side integral can be done even more easily. So that I think it should be left-hand side now. That is the line integral. So if I want to do the line integral, here I'm trying to integrate x squared y dx and y squared dy along the path. So if I open the bracket, if I open it, that means that here I'm integrating from 0 to 1. I'm integrating from 0 to 1. So why do I have 4 expressions? Before I explain to you why I have 4 expressions, let me see whether I have time to just do a quiz there. No, I don't have the time. Let me just give you the answer. I don't have the time to do a quiz here. If you look at the state where, first of all, go along this path. That will give us the first 2 expressions, and then we come back, along this path, so that we can traverse this path counterclockwise. So in the case of line integral, you can go this way and then come back here, or you can come back here and go this way. But you must go counterclockwise. And since each integral there gives you 2 terms. The first part gives you this term, and the second part gives you the second term. Let's see how it goes. So because you are integrating from 0 to 1, the first part, because y in the first equation is x. So where instead of y, you write x. So when you are integrating with respect to x, instead of y, you write x, because along the path, y is equal to x. The same thing, when you are integrating with respect to y, there's no problem, nothing to do, because it's only y you have, so you can perform the integral. On the second part, again, see how you interpret x squared y on the second part. On the second part, you see that x squared is y is now x to power 2/3. Remember that second part, you have that x squared is equal to y cubed. So if you want to see, if you now make y then x is equal and y is equal to x to power 2/3. X is equal to y to power 2/3. And then you change that to x is equal to power 2/3 to do the integration on the return path. So that is, and if you perform those integrals again, you just get this, and you get minus 1 over 44. So what we are saying is that no matter which way you go, the answer, see the number of ways we have done it, we are always getting minus 1 over 44. This one is the path integral along two paths. This is along the first path, and this is along the second path. Along the first path, x is equal to y. Along the second path, y is equal to x to the power 2 over 3. That's how you got this. From that point on, everything else is drudgery, which you can do over and over. Or you can take the double integral directly to mathematical, and it will give it to you. Okay, so let us go on. I have another question. The other question is almost exactly the same. Take on page 12 now. See, it is the same expression we had before. Evaluate the same integral, but along another path. Because it is important for you to know that once we change the path, we are getting another integral. For instance, you can see that once the path is different, the area inside, the area contained is different. So you cannot have the same answer for both of them, even though you are integrating the same function. So the given path is here, everything is remaining unchanged, except that here now, you now have the lower limit here is y to the power 7 over 2. And that is coming from the fact that x squared is equal to y to the 7th. Okay? So similarly, when you go to the other equivalent integral, you now see that y is equal to x to the power 2 over 7. So then, let me tell you the thing to watch out for. You see that in the second, the yellow part is down here, but it is up here. If you do not understand why it must be down here and it will be up here, let me know, because that is the critical thing here. Let me just tell you straight away. If you draw a line, if you draw a horizontal line, on the inside this domain, if you draw a horizontal line, you will see that as you are going along the positive x-axis, you first of all encounter the yellow curve before you encounter the blue curve. If you draw a horizontal line. But if you draw a vertical line, you encounter the blue curve before you encounter the yellow line. That is why what is up here is down here, and what is down here is up here. If you draw a horizontal, if you are starting from the x, then you are encountering the yellow line first before the blue line. If you are starting with y, you encounter the blue line first before you encounter the blue line. That is how to take your limits, because you must take your limit in the positive direction in both cases. So just be very careful when you are specifying your domain. And that is what this example, in simplicity, exposes some of the deep issues of multiple integral. And that's why I brought these two examples for you to see. So we can go ahead now and actually perform the integrals, which I have done for you. There's an error here as before, because I just simply copied. So this error here, I have to have 1 over 3 there. 1 over 3. 1 over 3, and this should be x cubed, because when we integrate s squared, we get 1 over 3 s cubed. So that is there from the current slide. So you can see that clearly there. And then everything else follows the same path, except that the path of integration is different. So it is only those evaluations, and everything here you have minus 5 over 92, minus 5 over 92. And then this is using mathematical to do the area integration. You get minus 5 over 92. And then going directly to the line integral, you get minus 5 over 92. So if you look at those, please do not rush over this thing. This is very important. Understand. If you do not understand this, you are going to pay over and over and over. It's a very simple problem. When it gets more difficult, you can dump it in the mathematical, provided you know how to specify your domain of something. Abdul Yusuf, do not raise hands in this class. Go to the chat room and drop a question. Okay, so that's how it is. So that's how it is. So I want to go to the next example. The next example is evaluate the integral, the line integral 2x minus y dx, x plus 3y dy along the closed path given by the ellipse x squared over 4 plus y squared is equal to 1. This is the ellipse, this is the path you are trying to integrate in. You're trying to perform integral on that path. So again, this is the given path is in the picture, the given integral is in the format of Green's theorem. And if we write mx is equal to 2x minus y and nxy is equal to x plus y, you do the partial differentiation of dm. If you differentiate m with respect to y, you get minus 1 here. And if you differentiate n with respect to s, you get plus 1. So you get minus 1 there. You differentiate this. Anyway, I don't know what is happening here. So you get, if you add the two together, you get 0. So that the m, the x, y minus the n, the x gives you 0. So the equation here, the expression here is 0, irrespective of path. No matter, it no longer matters which path you are doing, you are going to get 0. Christian, do I need to draw the curve before getting my domain? Well, if you can get your domain without drawing the curve, fine. But drawing the curve can be very helpful. So if you can get it without getting, if you can get the right answer without drawing, fine. You don't need to draw. But if you need some aid, most people need to draw before they can get it. But if you can get it, what is important is you get your domain right. If you give the wrong domain, you are going to get the wrong answer. Okay, so we've got that. So the answer there is 0. So the next one, oh, okay. Is that all I did? The next one is about something like that. I think integrating along the circle. This quantity gives you 0, and you get the answer to be 0. Don't think that every time it will be 0. So it just turns out in this particular case that the answers there are 0. My time is fast spent. I have to continue. I don't have time to waste here. I have to look at the excuse me. I have to look at the last thing that I prepared for you for today's class. Why didn't the limits of the second integral? Why did the limits of the second integral the previous question change? Why should it change? I'm giving you the same question because I'm just trying to show you that having the same question, as long as you go along a different path, you are going to get a different answer. I'm going to what it is what I'm trying to when doing the integral directly. Let me just check. Why did the integral of the second dy change? Okay, let's see the integral of the second dy. The second dy. Well, because the path is 0 to 1, it's still 0 to 1. I can't see. It's 0 to 1. There is no change in it. Anyway, I can't spend more time to answer you there. I have to go to the last issue that I've brought. I want to quickly introduce you to the concept of simply connected and multiply connected regions. A plane region is said to be simply connected if any simple closed path originally contained in the region can be uniformly deformed to a point without any portion of it leaving the original region. So if a domain is simply connected, just draw any closed path inside it. Can you shrink it to a point without leaving the region? If you can do that for anyone, no matter how large, no matter how small, then what you have is a simply connected region. If you can find a domain, a closed path that cannot be shrunk, the region is not simply connected. A region that is not simply connected is said to be multiply connected. The region shown in this figure is simply connected. So I repeat, a plane region is said to be simply connected if any simple closed path originally contained in the region can be uniformly deformed to a point without any portion of it leaving the original region. So because of that, this green area is simply connected, and you can integrate around it, and you can do several things with a simply connected region. The familiar theorem in a plane applies only to simply connected regions. So this thing we have been doing, we didn't say so before, but it is only correct in simply connected regions. So what we are going to do now is that we want to see, okay, what happens when the region is not simply connected. We assume in the simply connected region that it is possibly oriented. In this case, we are taking the line integral counterclockwise in the simply connected region as we have been doing. Now, take a look at this region. Imagine you have the same region, but there are parts of it that are not in it, that are not part of the region. So there are exclusion zones in the region. So you can see now, if you try to shrink this one to a point, you will pass through this one or this or both of them. And because these are not part of the region, we say that this region is multiply connected. Green's theorem does not apply in such a region. Can you tell me, please go to the chat room, can you tell me there are practical regions that you know that are multiply connected? Anything you know that is not simply connected, anything that is of importance that is not simply connected. Quickly go to the chat room. I'm not going to spend more than 1 minute here because time is gone now. Is there anything that is simply that is not simply connected that you know? Anybody? Anything you know? Donut, good. And if you cut a plane through the donut, then you have two concentric circles. A torus, yes, but you see a torus, a donut, torus, all these are three-dimensional objects. So you are looking at this, because we are talking of a plane now, you are looking at a section through it. Is there any, I want to see, I have something in mind. I want to see whether somebody will get it. Do you know anything? Nigeria is a simply connected region. French course. Okay, I think I know what you are talking about. A disk. Okay. Now, the region, the South Africa is a nation that is not simply connected because there are two countries that are completely inside it. A basketball hoop. Well, a hoop. I don't know. That is not a particularly good example, but I think I know what you are talking about. Now, do you know the cement block that we use to build houses in Nigeria? The cement block. If you take a section through it, that is not simply connected. Don't you know? Don't you agree with me? If you just take a section through a cement block, it's not simply connected. Now, Green's theorem does not apply in a region. This theorem does not apply to multiply connected region. But we are going to use the remaining time we have, which is like 7 minutes, to show you how we can now force Green's theorem to apply to multiply connected regions. We are going to do an artifice. So if we have 3 regions that are not a member, so you draw a channel to the boundary like this. You draw channels to the boundary. In order to apply Green's theorem to multiply connected regions, we begin with a simple artifice as shown. It is easily seen that the amended region is positively oriented. Notice that the contained parts are now traversed in a clockwise manner, while the containing region is counterclockwise. See me. If I want to go around the thing, you can see I am going counterclockwise now. Then I come in through this channel and I go clockwise, and I exit and I go counterclockwise again, and I come in through this channel and I go clockwise. Then I get out and I come here again, I go counterclockwise, and I enter this place and I go clockwise and I go out of that place. If you notice, you will see that the region is always on your left. Throughout the traversal, the region is always on your left, so it is positively oriented. The only problem now is that the region we have there is not the region we were given, because in the region we were given, there were no channels. If not for these channels, we would have been able to say this is a simply connected region. It is simply connected, but it's not what we were given. Notice that the content, that now in the artificially created positively oriented region, the simply connected region, we are free to apply Green's theorem. If we apply Green's theorem, we now have minus integral dm dy minus the n dx dA. You first of all going through the exterior one, even though you go through it in pieces. Then you go clockwise through C1, you go clockwise through C2, you go clockwise through C3. In the L11, the first, if we call this C1, if we call this first one L11, and then the other one L12, then this one L21, then L22, then this one L31, then L32. If you take all these straight lines like that, so when you get there, you go along 6 lines in addition to 3 close paths. So you get 1, 2, 3, 4, 10 integrals. And so instead of just a single integral on your right hand side, you are going to get 10 line integrals. Like j, I goes from 1 to 3, and j goes from 1 to 2 is the jth line connecting the ith part to the containing part as shown. So you have a complicated result for the Green's theorem. Remember that the contained regions, the line integrals are taken clockwise for us to have a positively oriented surface. Ordinarily speaking, the artificial region we have created is different from our original region. Is there anything we can do to make them approximately equal? Sorry, time is fast spent, but I want to see whether half a minute, whether anybody will tell me if there's anything we can do to make them approximately equal. What can we do to make this region that I'm seeing here approximately equal to this? What can we do to make them basically the same? What can be done? Is there anybody? Shrink the width of the channels. Good, good, good. That is Orobosa Isokwu. I hope I'm correct, pronouncing your name correctly. Orobosa Isokwu. That's very smart. So you see what we are going to do? We created this ourselves. So why can't I move this one as close to this as possible so that the limit as the distance between these two tends to 0? This one will always, and those two integrals will always, with those two line integrals will be the same, but opposite directions. So they will give you, they will cancel each other out. These two, when you bring them too close, they will cancel each other out. These two, when you bring them so close, they will cancel each other out. So you're now left with a counterclockwise integral on the outside and clockwise integrals on the inside. So instead of 10 integrals, you now have 4. You have 1 on the outside and 3 inside. So that is what you now have here. So you have that your integral is the main integral outside counterclockwise, and the integrals inside, 3 of them, 1, 2, 3, that is clockwise. So that is what you get. So we can write the above equation more compactly when the number of included regions are n in number. So instead of just doing them one by one, you say the summation from I is equal to 1 to n of these line integrals. Always remembering that the line integrals inside are taken clockwise, while the enclosing one is taken counterclockwise. Special case. Imagine a situation where the m dy is equal to the n dx. So that means that difference is 0. When that happens, that means that this term vanishes. This term vanishes, and you have these two on the same side equal to 0. So if you carry one to the other side, you have this last expression. You have this last expression, and then this last quiz now, which you don't have to do because our time is gone. I'm giving you a last quiz. Time is gone, so that is the last slide, I think. So take that one and answer that to yourself. Only one of the 5 answers is correct, and this is a typical. This question is going to be in the questions database. You are going to face it, so better answer it correctly now. I won't tell you what the answer is until next lecture, or if you put the question online, I will answer that. So this is the end of today's class. Have a nice day.